They're fast. They're intelligent. They're deadly. Soon, they'll be everywhere. Robots and living machines are breaking out of the laboratories and stepping into our lives. Will they help us? Or will they replace us? Even the people who create them can't agree. But whether humanity likes it or not, the robots are rising. And our world will never be the same.
No, not that. You, I suppose you're programmed for etiquette and protocol.
Protocol? Why, it's my primary function, sir. I am well versed in all the customs. That is why I have been programmed.
What I really need is a droid who understands the binary language of moisture evaporation.
These are the robots of our dreams. Intelligent machines that live to serve.
Can you speak Bocce?
Of course I can, sir. It's like a second language to me.
And these are the robots of our nightmares. Mechanical predators hell-bent on replacing their creators.
I think the idea of people fearing robots is almost a myth. I'm not so sure that people imagine that robots will bring direct harm to them, but it may be the cultural changes and the changes in the way we do things may have impact or consequence in people's lives or workplace or the way that we do things. And it's that notion of change that seems to be the great concern.
A robot is a machine that performs useful actions and is capable of making decisions about its behavior. In other words, robots are the love children of computers and power tools. They come in all shapes and sizes, each specific to its function. As we shall see, some of them even resemble the artificial humans of the movies. But until very recently, robots in the real world looked more like toasters than the Terminator. Since they first came on the scene in the 1960s, real-world robots have slowly worked their way into industry, taking over more and more dirty, dull, and dangerous jobs with each passing year. In assembly line businesses, such as building cars, the ability of robots to perform complicated tasks over and over is a perfect fit. But getting robots off of their pedestals and into the world at large has proven far more difficult than science fiction films would have you believe. This is beginning to change. The revolution in computing power, combined with unorthodox new approaches to building robot brains, has resulted in a revolution in robotics technology. In the near future, the worlds of fantasy and reality may converge. When that happens, will we be ready for it?
RoboCop.
You better back up, pal!
Your move, creep.
This is the fantasy vision of police robots. And this is the reality. In Washington, D.C., the U.S. Capitol Police raced to the site of a suspected bomb. The Capitol Police are charged with protecting Congress, much as the Secret Service defends the president. These officers have to be more cautious than ever before. Terrorists have begun to plant 2 bombs at their target sites. The primary bomb explodes first, followed by a secondary device that's left to kill the policemen who come to investigate.
Things have changed a lot. We talked about secondary devices for years, and now we're starting to see them on actual incidents in the U.S. They've been common in Europe for some time. And the degree of sophistication has increased to the point where there are literally proximity devices, which used to be limited to military explosives that explode when you approach them. They just sense a change in the magnetic field and off they go.
What's it look like? Well, it looks like a box. Wooden, about this big.
When an experienced officer identifies a suspicious package as a bomb, the police take no chances. They send in the Andros 5. The Andros 5 robot has become the tool of choice for bomb squads in high-risk areas around the world. The robot's popularity is a sad reflection of the increasing danger of law enforcement. The machine is teleoperated, which means that its actions are controlled from a safe distance by the bomb squad. Guiding its multiple claws and cameras takes practice, but most officers feel it's worth the effort.
Actually, I'd like to send the robot in every time. It makes my job a whole lot safer. And I think our job is relatively safe with our training and equipment, but there's that word relative, and there's zero risk in sending the robot in. And if the robot bites the dust, well, I'm still here to requisition another one, and I've got all of my extremities to do it with. It's just a mechanical loss.
Now comes the most critical part of the operation. The robot must drop the bomb into a custom-made sphere that will absorb the shock of an explosion. Somewhere in New Mexico, a fighter-bomber has crashed. The military needs to get a nuclear weapon out of the burning wreckage. They send in a robotic Humvee. These are the jobs that robots are beginning to take on. Jobs that literally nobody wants to do. Again, it's what roboticists call the 3Ds: dirty, dull, and dangerous work. Like the Andros 5, this robot is teleoperated. The Humvee can drive largely by itself, but its arms are completely controlled by a human operator. This is the key question of robotics. How smart does the machine need to be? The answer most roboticists give is simple. It must be smart enough to get the job done. In some cases, you wouldn't want to trust a machine to do everything. But the strain of controlling every tiny movement from afar is often too much for teleoperators, especially if there's a time delay between human action and machine response. The newest robots use the faster, cheaper computers available today to let robots think for themselves, at least up to a point. There are 3 basic ways to make robots work. An intelligent, teleoperated system has some computerized control at the robot end, but a human makes virtually all of the decisions. With supervisory control, the human makes key decisions about what the robot should do, and the robot has enough intelligence to perform its tasks without constant guidance. An autonomous robot is virtually free of human control. This might not always be a good thing.
Tobor, the most amazing, the most fantastic creation of man's mind.
Oh, he looks alive.
Tobor, bringing you chills you've never known before.
People's perceptions of robots as compared to what they really are is one of the biggest problems that we have to face as roboticists, because Hollywood keeps on perceiving these robots and projecting them as competent, capable machines that will take over your world when you're not looking. When in actual fact, it's very hard for a robot even to get its steely butt off the ground, let alone wander around a room and actually do something like, say, vacuum it. The real future for these things, we feel, is when we can finally break that barrier, when you can finally take machines away from the little boxes that we have to put them in, like factories or even computers, and give them the power to be able to interact in the real world.
In the mid-1990s, the two Dante robots became famous for their adventures out in the most remote parts of the real world. These 8-legged tethered machines climbed into active volcanoes in Alaska and Antarctica. The first Dante broke down almost immediately when its fiber optic communication line froze and snapped. The second robot fared much better. For days, it crawled around a volcanic crater, sampling toxic gases.
Heading, I think we're ready to stand up and try stroking and turning.
Dante was controlled using satellite links to the continental United States. The machine received basic instructions, then slowly plotted out its descent into the crater. The mission was overseen by NASA robotics chief Dave Lavery.
With the Dante projects, basically I was responsible as the NASA telerobotics program manager for being the NASA representative for both field parties, Dante 1 and Dante 2.
Get a second heading, give us your tether payout.
The real significance of both projects, one, it was a demonstration that the technology associated with the robotics was ready to make the leap out of a laboratory environment into a real, harsh, realistic setting. And you can't get anything that's more harsh than a polar volcano as far as we've been able to find on this planet. And yet the robotics technology has shown that there's a capability there for safely delivering a science package into a volcano interior and then bring the data back out without endangering any human lives.
Dante was a product of Carnegie Mellon University, the headquarters of one of the major figures in robotics today. Red Whitaker is a former Marine who has made it his life's work to build robots that can function in harsh environments. He is the de facto leader of the top-down approach to robotics, which mimics the way humans, the animals at the top of the food chain, interact with their world. Whitaker's robots are programmed with an advanced knowledge of their surroundings. Every action they take is carefully considered and weighed against an overall plan formed by their computer brains. They are also notoriously big.
I've already been thinking ahead to next design on this thing, and something more monolithic, maybe get the... My first 50 robots probably have the rap of being the mega robots, the big guys that Red builds big machines. And whether it's a mouse or a moose, the thing that's important is that it's appropriate to its purpose. I was a little restless in my world, looking for something different and more, and computing was already a little far along. I sought something that would be pioneering, true invention and creation, and also good for decades, and something that would impact, make a difference in my lifetime. I chose robots. The real galvanizing event was taking on development of the machines to clean up the 3 Mile Island nuclear accident, and that experience then set the course of a career.
Whitaker's company, Red Zone, has made a full-time business out of building robots that go where humans fear to tread. This is Rosie, a robot that decontaminates and dismantles aging nuclear facilities. In a few days, Rosie will be sent away to tear apart a reactor near Chicago. Rosie costs $750,000. Once she goes into service, she's expected to function without failure. no one will be able to fix her when she's radioactive. Houdini is a red zone robot that works at the Oak Ridge nuclear weapons plant. After lowering itself into a hazardous waste tank, Houdini uses a dozen different tools to scoop up and store away sludge so lethal it could kill most of the life on Earth. Whitaker's robots are very functional, but he will admit, they aren't very glamorous.
In the early going, things were simple. Form followed function, and the only challenge was to get a robot to navigate or clean up a nuke setting or to perform an industrial task. Now people actually expect robots to look like robots and to speak like robots. The Ambler robot behind us did in fact think about where it would move, that it would be moving its left foot forward and then crowding the next obstacle to leave room for the right foot to get up and on, and actually to express what it was doing and what it was about. And people actually were enchanted by that. I think that next generation robots have to master that kind of speech and interaction a lot more than their personal status or the weather report, but to really interact in the way that we are right now.
Whitaker's early robots were among the first that could function outside of a laboratory without constantly breaking down. But apart from Whitaker, no one had much luck making robots that could reliably find their way through unpredictable environments. And no one at all could make their machines move quickly. Then along came Rodney Brooks, the inventor of the bottom-up approach to robotics, which mimics the behavior of creatures at the bottom of the food chain.
Back in the early 80s, robots were very, very slow. They were connected to mainframe computers. They would compute for minutes at a time before the robot could move even a meter. And if anything changed in the world in the meantime, they were completely lost to what was going on. And I looked around at insects, and insects, could fly around at a meter or so per second. They could avoid getting eaten by a bird. They could chase prey they're after. They could go through mating behaviors. So it seemed to me that maybe we were organizing the computation the wrong way, in the way we were approaching robots. And that maybe by trying to organize the computation a little more like it's organized in insects, we would get much better performance.
Brooks' insect robots aren't intelligent the way we think of humans or even computers as being. Instead, they operate on patterns of behavior. When you turn them on, they're brainless. But with each step they take, they learn how to adapt to their environments. Rather than having a standard central controller, these robots have separate layers of behaviors that are independent but which communicate. No advanced behavior can start unless the simpler ones are up and running.
When I first started talking about these ideas, the only good thing going for me was I had videotapes of robots really doing things that other robots weren't doing. Otherwise, it would have been dismissed as a total flake, and probably would have been a total flake. But because I had some performance, people looked at it and thought, well, maybe there's something there. But there was still a lot of arguments with me and a lot of resistance. Now, over time, people who actually build robots have generally come to accept this approach at the low-level aspects of controlling a robot, and it's become the standard way to operate.
Unlike Whitaker, Brooks is not an engineer. His specialty is building brains. The robot's bodies are made by his colleagues and students at MIT. But like Whitaker, Brooks is ambitious and not opposed to making money. Brooks is now chairman of IS Robotics, the bottom-up version of Red Zone.
How are the new tracks going?
I guess
Virtually everyone on staff is an MIT alumnus. They all share the dream of putting a robot in every living room.
This week or next week we'll get that set.
But right now, many of their robots are paid for by the people who brought you duct tape and the internet, the United States military. The IS concept is to build swarms of small, inexpensive robots that can cover terrain too dangerous for troops to enter. This minesweeper is designed to be carried by soldiers into combat zones. The controls are strictly supervisory. The machine finds its way through the world in the same brainless fashion as Brooks' insect robots. Ariel is an underwater minesweeper built for the Navy. The idea is that before soldiers hit the beach, dozens of these robots will march in and sacrifice themselves on enemy booby traps. Ariel's body was based on a crab. If currents throw it about, it can operate upside down. IS also sells versions of the Genghis robot to labs around the world. The original Genghis launched the insect robot revolution. It was built by Colin Angle, a one-time grad student of Brooks who is now head of IS. Angle and Brooks believe the entertainment market could provide the monetary push that commercial robotics needs. Much as computer games helped finance the microprocessor boom, a must-have robot toy could fuel the next high-tech revolution. This robot baby doll might be the start of something big.
So the doll is capable of sensing lots of different interactions. Before it gets too upset and really all it wants to do is nap and eat, we can demonstrate some of these things. Like he likes to play patty cake. He can. He's just singing a song that he sings when he plays patty cake, and he likes. You can see he's kind of like that. He also likes to bounce. But of course, bouncing the baby like I'm doing, also is very tiring for the baby. So as long as I keep doing it, he'll be in a good mood. But if I stop like I did, he's going to very, very rapidly get upset.
And cry.
So we should give him his bottle rod. Why don't you demonstrate that?
Yes, he's not being real happy right now. Oh, that's better. That's much better.
Well, we've instrumented the doll with a number of different sensors. Like inside the body, there's a ball in a cage, and we can sense where that ball is and where it's moving, and we can detect rhythms. So we use that to determine rocking and orientation, and if Rod was to hold it upside down, it really doesn't like that, and it's going to start. It'll fairly quickly start to cry. And so that puts in a really bad mood.
We really did upset it by holding it upside down, because it's got these various drives that need to be satiated, and certain emotions that get excited by both good things and bad things.
Just give it a hug.
And the hugging sort of lets it get a little happier.
It's a very reassuring and comforting sort of thing. So you can see we've improved his mood measurably by giving it a little TLC here.
In robotics, a lot of us feel like we've been cheated by Hollywood, in that Hollywood has shown robots doing things that we don't have any possible capability of doing with our robots right now. So people are disappointed when they see our real robots. On the other hand, I'm more optimistic now than I was 5 years ago that we're going to eventually catch up with Hollywood, and maybe before too long, maybe even in my lifetime, be doing a few things that Hollywood hasn't thought of just yet.
Like what?
Oh, I haven't thought of them either. Leave it as a mystery.
The animal kingdom is filled with millions of different designs for creatures far more capable than today's robots. But as Rodney Brooks has shown, building machines based on lower forms of life is a promising path on the road to the ultimate goal, creating an artificial human. The ongoing miniaturization of computer processors and parts has resulted in the first wave of machine copies of organic life, what science fiction films call replicants. And nobody builds replicants as well as the men and women at the Massachusetts Institute of Technology. MIT's Leg Lab is constructing a motley assortment of replicants, ranging from robotic flamingos to creatures that defy description.
Robot's the official name.
Rob doesn't like that.
It doesn't really have a name. In our laboratory, how to name the thing. Sort of like naming a child, you know.
Okay, here we go.
The secret to getting these machines to run, walk, and hop is a combination of nuts and bolts engineering and savvy software writing. This one-legged robot has no onboard computer. It's kept upright by pure physics. But when the robots have multiple legs, they're propped up by something called virtual model control. The machines are tricked into keeping their balance by a simulated spinal cord built into their computer brain. The virtual spinal cord lets this robot, called Spring Turkey, walk on 2 legs. Until recently, this was considered impossible. But the Leg Lab tackles the impossible every day. For instance, Peter Dilworth is trying to bring dinosaurs back to life, working from the skeleton of a troodon. He has painstakingly assembled a 2-legged robot that he hopes will walk and run like the monsters of the Mesozoic. Ultimately, he would like to build a zoo filled with dinosaur replicants. Like many young roboticists, Dilworth's work has been inspired by science fiction.
One of the things that really got me interested was this little guy. This is the robotic soldier from Star Wars. The whole idea of seeing these robots in the movies convinced me that it must be possible to actually make them. They look so real, and I felt that, you know, why can't I make that? Why can't I bring that into existence? The trick of making a robot walk is being able to control forces on the legs, at least as far as walking bipedally, walking with 2 legs is concerned. I mean, there are robots with 6 legs, hexapod robots that can walk and crawl, but they're statically stable. But in the case of this robot, a biped robot, the balance of the robot is much more complex. And in order to maintain balance, you need to be able to push against the ground very carefully, you know, with just the right amount of pressure. And you need to be able to sense how much pressure you're feeling on your leg, because that information, the sense of how much force you're using, is an important part of figuring out what your balance is.
Replication doesn't just mean imitating a creature's physical movements. It can also mean emulating the way they behave. Creatures like ants, which are driven entirely by instinct, manage to accomplish great feats by pooling their limited intelligence. Could the same thing happen with machines of limited intelligence? James McClurkin has studied the way that insect colonies function by building robot ants that communicate using infrared devices. The robots signal each other if they find food, and they learn to cooperate to solve simple problems.
When you make robots small, you have a lot of advantages due to their size. You can put them places where you can't get larger robots. You could have them foraging around through nuclear power plants, going through pipes, looking for cracks. You could even put them in the human body, use them for surgery. We were being funded 2 years ago to work on surgical robots about this big. They would go through your large intestine and perform surgery. So small robots are good. The only problem is that when you have small robots, they tend to be small. So one of them can't get very much done. You like to have a community of them working together to run around and collect dirt from under your refrigerator or spy in a building. In the building, you'd want, at the very least, all of them to avoid each other, so you wouldn't all end up in the same room.
But some of the most promising work in replication is focused on the most diverse forms of life on Earth, the creatures of the sea. Mankind has long marveled at the grace and power of fish, which can propel themselves through ocean waters at great speed with minimal expenditure of energy. Wouldn't it be nice if we could take all of our sophisticated sensors and pack them into something small, fast, and capable of swimming the ocean? Something, for instance, like an artificial fish. This is MIT's Department of Ocean Engineering, the home of Robo-Tuna. The tuna, known as Charlie, is used to study how fish propel themselves through water at great speed. Modeled after the bluefin tuna, the fastest fish in the sea, Robo-Tuna looks and swims just like its real-life counterpart. It also squirts out a trail of phosphorescent dye that lets scientists analyze its underwater contortions. Ships and submarines of the future will incorporate the swimming lessons that Charlie is teaching. Robo-Tuna was such a success that it spawned a free-floating follow-up, Robo-Pike. Robo-Pike has a fiberglass rib cage that is wrapped in foam and lycra. Its movements are powered by 3 motors that drive an elaborate system of internal cables and pulleys. These duplicate a real pike's muscles and tendons. Affectionately called Wanda by its chief designer, John Kumpf, Robo-Pike is a great leap forward in the quest to build a genuine replicant.
I was an undergrad walking through the halls at MIT, and I saw a sign on the wall that said, "Come work on a robot fish." And so I don't know, I knew that project was for me. I never thought it would, I never guessed, but I was already into robots, and I already worked a little bit in the field, and it looked like a much more interesting project than most of the stuff out there. Most of the robots out there are kind of boring, like welding robots, or, they're just not, they didn't quite have the draw that this does. Pipe is going to be used to help us learn about swimming, and eventually we're going to do something like throw it into the ocean and ask it to go follow fish around and tell us what they do. And how come we can't get our craft to go through the water with as little energy as it takes for a fish to do it? I mean, what can they do that we can't, And so part of the mission of the Pike is to figure that out, is to tell us, we can output sensors, and we can put computers on board and collect data, and we can find out exactly how this body and this undulating, this articulated mechanism, which is just like a fish, interacts with the water. So, nature already knows the solution. We have to go find out.
On a warm summer evening, John takes Robo-Pike for its first trial swim in Boston's Charles River.
When you start to approach a problem like this, you just develop a new respect for what goes into a living creature, and how amazingly they're put together, and how they're filled with creativity and of a sort that makes you wonder if there really is a God.
It's early in the morning off the coast of Northern California, but the good ship Point Lobos has been underway for some time. Its mission is to bring a deep-sea diving robot called the Ventana to the site of an ocean research experiment. The Ventana is an ROV, remotely operated vehicle. It is equipped with 7 cameras, 4 onboard lasers for targeting, 2 robot arms, and an assortment of interchangeable claws and power tools. It's one of the hundreds of ocean-going robots in use around the world. ROVs are usually pressed into service by oil companies looking for offshore petroleum. But the Ventana is special. It belongs to the Monterey Bay Aquarium Research Institute, a non-profit group funded with a hefty grant from the late David Packard of the computer giant Hewlett-Packard. The group, known as MBARI, conducts pure oceanographic research. They're trying to learn more about life in the darkest, most mysterious parts of the ocean. The Ventana regularly dives to depths of 5,000 feet, where the pressure is so great it could implode a human being. The pressure problem is compounded by the fact that the robot is an electrical device operating in deep water, so a leak would be catastrophic. Normally, the Ventana goes out on picture-taking missions of ocean life. Today, however, it's installing a scientific instrument in a canyon wall at the bottom of Monterey Bay.
Well, see what the lasers are right now? That's our seismometer site, that hole right
The
there.
mission is flown by a crew sitting in the belly of the Point Lobos.
Can you hold it here?
Yeah, go ahead. Just go ahead and zoom. I want to see how close we are to the wall. Yeah, there you go. That's good.
That's not a bad area.
Medium oil right away.
Well, right now, the ROV is balancing on a rock. So we have 5,000 pounds of vehicle trying to hold station.
You can do that?
Standing up on, just touching in one place on a rock that's sticking out on the left-hand side here. And while we're balancing on the rock, another pilot is controlling the manipulator.
Yeah, see, I can't swing anymore.
And trying to.
So what do you need me to do? Fly up in there?
Cylindrical housing that would hold a seismometer into the
Lateral
hole.
to starboard?
Yeah, I need.
He's got it.
Yeah, it's going.
MBARI does not operate any manned submersibles. They believe that robots are the future of deep-sea exploration. Humans will remain safely above water, or even on land, while their robot proxies plumb the depths of the abyss. The same approach is being used to help mankind explore another inhospitable region, the black void of space. Santa Monica, California is a far cry from the vacuum of space, or even the surface of the moon or Mars. Yet it's here that roboticists have gathered for a planetary rover roundup. Near the fogged-in beach, some of the best engineering minds in the world present a gaggle of wheeled, tracked, and legged devices that they hope will one day cross the sands of other worlds. They look slow and somewhat clumsy, but the fact that they move at all is a technological triumph. Rovers have to meet a set of requirements even more demanding than undersea robots. They must survive being shot into space, land on other moons and planets, and then operate in an alien environment for extended periods of time. If they break down, they're a long way from help.
I think this will conclude my demonstration. Thank you.
For this and many other reasons, most rovers move very slowly. A rover whizzing across terrain in low gravity could bounce on a rock and fly over the side of a cliff. This is good engineering, but it doesn't make for much of a spectacle. Still, these machines are the best hope the human race has in the next few decades to expand its knowledge about the origins of the universe. Manned space missions are now considered too dangerous and expensive to mount. Robotic astronauts will have to do our exploring for us.
Fundamentally, these rovers that you've seen today, some of them are designed for the moon, but largely we're looking at rovers that are designed to go to Mars. The pan and tilt mechanism
15 years ago, we were really worried about simple little controls. How could we get it to do this little task or that little task? And today we actually handle most of those. You know, there's a whole realm of things that have to do with obstacle avoidance, which we still worry about, but is pretty well in hand. We pretty well understand how to do it. Now we have environments that are just wonderful for controlling a robot to get and do a task. And partially it's driven by advances in software and especially the advances in computing technology. Being smaller, cheaper, more powerful, lighter, it's just massively influenced what we're doing.
The vehicle that you see out here now.
Robotic explorers have actually flown in space for decades, bringing a set of eyes and ears to places human beings could never dream of visiting. The robotic space pioneers included America's Mariner, Viking, and Voyager, and Russia's Venera and Lunokhod. These celestial emissaries sent back the first close-up pictures of other worlds. They forever changed the way we see the universe. But the early probes had little onboard intelligence. At the time, computers were bulky and slow. Almost all spacecraft actions were controlled from the Earth. The next generation of space robots are smaller and smarter. They have enough brains on board to take orders without second-to-second supervision. Mars Pathfinder was the first of a series of missions that NASA is sending to Mars roughly every 2 years. Pathfinder carried the Mars Sojourner, the first rover sent into space. Sojourner landed on Mars July 4th, 1997, thus becoming humanity's first semi-intelligent emissary to another world. At NASA's Jet Propulsion Laboratory, Rocky 7 is making its way across a rock-for-rock recreation of a Mars landing site. This rover is a great technological leap over Sojourner. Packed full of sensors and downsized computing power, Rocky is built to do much of its work without constant human guidance. In this case, a NASA controller sends Rocky a message saying, "Take a look at these 5 rocks and get a soil sample." Rocky works out for itself how to get to the rocks and what to do when it arrives. At the end of each mission, it will download its data to Earth, then wait for its next assignment. Eventually, fleets of small, inexpensive rovers could roam Mars and the Moon, paving the way for human pilgrims.
Robots have a number of different roles for space exploration. Probably the one that's most significant is to be a precursor for eventual human presence, especially on planetary surfaces. This is the idea where you want to send a robot, for example, to the surface of Mars to do a survey to find out what the chemical composition of the soil of the planet may be, to see if there's a way we can process that soil to get life-sustaining chemicals for the humans to utilize when they get there eventually. Then later on, they can actually be doing surveys for potential human landing sites or even preparation of a human habitat. So basically, a human flight that may come 10 or 15 or even 20 years later will have their house already built, sitting on the surface of Mars, waiting for them to just open the front door and move in and live.
This is the Space Systems Laboratory in College Park, Maryland. The SSL is building the Ranger space robot for NASA under conditions that reflect the realities of government budget cuts. Ranger is being largely designed and flown by a small band of enthusiastic scientists and grad students at the University of Maryland. Its parts were bought at hardware stores or handmade by the students themselves. Today, the team is placing Ranger into a water tank for a practice run of a mission it will soon fly in outer space. Serving as a kind of remotely operated auto mechanic, Ranger will float outside the International Space Station, performing tasks such as unscrewing panels and replacing parts. It's designed to reduce the number of hours astronauts have to spend on dangerous spacewalks. After NASA announced Ranger, Japan's National Space Development Agency declared that it had designed a similar robot that would be launched first. ETS-7 is being built by 3 of the biggest companies in the country. Japan wants to beat the U.S. to space with a telerobot for a simple reason: money is at stake. Robotics is a major growth industry, and the Japanese want to hold on to and expand upon their market. Their view is so long-term that corporations are working on the details of using robots to build settlements on the moon within the next 30 years. Rovers are also part of Japan's effort to restake humanity's claim on the moon. Later versions of this unique three-wheel design have a good chance of roaming across the lunar soil, searching for valuable mineral deposits. The US and Japan are in a semi-friendly technological Cold War. Like the US-Soviet race of the 1960s, space is the initial place that this high-profile technology will be put on display. But no matter what nation owns the hardware, the result will benefit us all. The massive streams of data flowing back to Earth from our robots will let us see the universe in a unique, new way. Through the eyes of our spacefaring explorers, we'll know what it's like to float amongst the stars. You're looking at the world of tomorrow, as envisioned by survival research laboratories. SRL is a San Francisco-based performance art group. Their malevolent machines spurt napalm and battle to the death before audiences across the world. The group takes Army surplus ordnance and retools it to create these Roman circuses of destruction. It's a black-humored parody of military Megadeth technology. But it is also a bleak vision of an apocalyptic future in which hunter-killer machines run wild. In the wake of the high-tech carnage of the Gulf War, it's not difficult to imagine that this cybernetic slaughterhouse could soon be duplicated in real life. But at the moment, battlefields ruled by autonomous robotic predators lie in the distant future. This is not to say that the wars to come will look anything like the wars of the past. The killing zones of the future are changing because the line between fighting men and fighting machines grows thinner every day. For all practical purposes, these soldiers are cyborgs. They are fully wired into the electronics attached to their bodies and built into their guns. They always know where they are and where their enemies are. Information is now a lethal weapon. Robots will have a place in this plugged-in battlefield, but they won't be pulling the trigger.
The idea of autonomous or even semi-autonomous killing robots is extremely difficult to imagine for a variety of reasons. It's difficult to imagine even very advanced future robots being able to develop the sort of flexibility and cunning that a human being would be able to exhibit, the ability to address and deal with novel situations and unforeseen circumstances. Robots, machines are capable of seeing things in terms of black and white, ones and zeros, whereas a human being is capable of seeing things in shades of gray, and that's really what is required for that sort of mission.
Military tradition is another barrier to putting killer robots on the battlefield. Since the dawn of civilization, great armies have been built around the skill and spirit of their fighting men. The idea of handing over the waging of war to machines does not sit well with professional soldiers. For this reason, most military robots today are unarmed spies. At Sandia National Laboratories, engineers have built a fleet of tele-operated robots that navigate hostile terrain and ferret their way deep behind enemy lines. Most of these machines are intended for use as scouts, ground equivalents of spy satellites or reconnaissance planes. Miniature rovers have their place here, too. Their small size gives them access to areas that human spies find hard to penetrate. The same robotic control systems now being put into cars and trucks are finding their way into tanks. Supposedly, these will be used as decoys, though it's not hard to imagine a fully armed, tele-operated tank rolling across a battlefield. The Army, of course, isn't talking. Sandia's Fire Ant is a tele-operated robot with fangs. The vehicle drives out to a lonely spot, then waits for its prey. Unmanned flying robots are increasingly common in today's Air Force. Drone planes have flown since the Second World War, but today they're flying at all altitudes, often for days on end. Here, too, their primary mission is collecting intelligence. They provide continuous real-time information about the battlefield. But the best-known flying robot is also the deadliest. Since their introduction in the 1950s, cruise missiles have proven themselves easily as lethal as the Terminator, and perhaps a bit smarter. They can fly at rooftop level for hundreds of miles. They make decisions about their course, changing direction as they encounter obstacles. And they are notoriously proficient at finding and fatally striking their targets.
The technology component of military operations has continued to grow over time and will continue to as our technological sophistication as a society and as a world increases. That does not suggest, however, that the future battlefield will be empty of human beings and wars fought by machines against other machines. The more likely scenario is human soldiers working alongside robots, sort of in tandem, and the military is only just now beginning to explore where the synergies might be found of using robotic systems with human soldiers.
The Sega Joypolis is a two-story, state-of-the-art arcade in Tokyo's Shinjuku district. Using a combination of robotics and high-definition visuals, Sega has put hundreds of realistic simulated experiences under one noisy roof. For most of us, entertainment is the first place we will have up-close and personal encounters with new robotic systems. The technology that powers these machines is being built into the consumer electronics of tomorrow. It includes high-resolution screens, adaptive audio, artificial intelligence, and advanced haptic interfaces. Haptics is the word roboticists use when they mean the sense of touch. These children can actually feel the pull of a virtual fish on the other end of their line. The key to Sega's success with these simulators is the way that real-life objects are integrated into an artificial world. Game players sit in genuine racing cars or hold onto real skis. But the rest of the experience is created by computers and robots. These machines sense your movements and respond to your actions. The synthesis of man and machine is nearly perfect. All of this has been made possible by the ever-increasing power of computer processing. This plant makes Pentium processor chips for Intel. It cost $2.5 billion to build, and most of the chips it's making today will be obsolete in a handful of years. According to the rule of thumb made famous by Gordon Moore, one of Intel's founders, processing power doubles every 18 months. 10 years from now, one CPU could have the processing power of every computer on Earth today. This incredible progress is the result of a whole new realm of engineering, building machines at the microscopic level.
Silicon micromachining, which wasn't around just a few years ago but is now becoming very common, is going to have a big impact on robots and are going to let us get a lot closer to the sort of sensor density that we see on animals, on insects, where a cockroach has 30,000 air-sensitive hairs on its legs. With conventional technology, we couldn't put that density of sensors on a small robot, but with silicon micromachining, we will be able to.
But for truly extreme and potentially world-changing robotics, we need to drop down another 1,000 times in size, down to the level of nanometers. Nanotechnology seeks to build machines at the molecular level. Imagine a factory such as this, shrunk way, way down. Thousands of such super small factories will assemble tiny robotic construction workers. The nanorobots will then tear apart and rearrange the atoms of whatever materials they're given. Nanorobots would be the ultimate recyclers. Just take yesterday's trash, throw it into the nanoprocessor, and out comes a sofa. But nanorobots could just as easily be programmed to turn your body into a pool of jelly. But this is the most extreme and perhaps far-fetched vision of nanotechnology. The practical work being done today is seen in this computer simulation from NASA. It shows how we might build materials that are atomically precise. This would result in lightweight, super strong metals, plastics, and even diamond-hard surfaces that could revolutionize everything from medicine to space travel. At NASA's Ames Research Center, the mightiest parallel processing computers in the world are being used to solve nanotechnology's enormous technical challenges. This research is still in its early stages. Working nanotechnology might not happen for a long time, or it might not happen at all.
A lot of the critics are saying is this is really hard, and it is really hard. But there's a couple of reasons we think that it's possible. First, if you look at the physics, nobody's been able to say, look at this physics, you can't do it. Number two is we have an example of atomically precise replicating machines, and that's life. The cell is programmed with DNA and environmental factors. It replicates. Life can build trees and whales and grass and people and dogs and whatever. So sort of life is the existence proof that being able to build atomically precise products and put them together and use replication is a very, very powerful mechanism.
If the idea of self-replicating machines seems unlikely, one need only turn to Japan for a larger-scale look at the future. In the foothills of Mount Fuji, Fanuc Industries manufactures industrial machines. The ratio of humans to robots in this plant is approximately 100 to 1. Humans supervise, but these machines actually build themselves. Our robots have the ability to reproduce themselves. If they also become highly intelligent, we must begin to ask whether or not they are now alive. The advent of new technologies makes the creation of new life forms, including artificial humans, more and more likely with each passing day. All over the world, robots are moving out of the laboratories and into our lives.
Xavier here. I just stopped to say hi.
But for some roboticists, these pragmatic designs are just small steps along the path to the Holy Grail, the creation of an artificial human. Whether they're called robots, androids, or humanoids, artificial humans have captured the popular imagination since they were first envisioned in the 1920s. Typically, humanoids are cast as soulless embodiments of the mechanical age, symbols of our dehumanization. Movie robots are often strong, silent types, devoid of emotion and loaded with firepower.
But he's a robot. Without you, what could he do?
There's no limit to what he could do. He could destroy the Earth.
But a few friendly faces have worked their way into popular culture.
You must come along now, Artu. There's really nothing more we can do. And my joints are freezing up. Don't say things like that. Of course we'll see Master Luke again. And he'll be quite all right. You'll see.
Perhaps these creations of fantasy are reflections of our mixed emotions about technology. Building a humanoid in the real world is a lot harder than the movies make it look. And putting brains in the package is harder still. But we seem compelled to try. For centuries, our curiosity about the intricate machinery of life has driven us to create mechanical versions of ourselves. The finest artificial humans of the industrial age were the clockwork automatons of the 18th and 19th centuries. Watchmakers and engineers tinkered together these lifelike figures from tin, cloth, and ceramics. Their realistic movements were driven by the same wind-up mechanisms that power grandfather clocks. Automatons were usually built for entertainment, but some believed that if they built exact replicas of human beings, and they imbued their replicas with the power of movement, their creations might just come to life.
All right, now, Electro.
Electro was a mechanical man built by Westinghouse. His appearances at the 1939 World's Fair made him the most influential humanoid of the 20th century.
Well, he's almost human. If he wasn't so big, I'd take him for an engineer.
Now, Electro, a moment ago you were bragging about being able to count on your fingers. Do you remember that? Well, we're going to find out about that. Now, do you remember how many children were born at the same time to a certain family up in Canada? Do you remember that? All right, let's see if you do. Count them on your right hand. 1, 2, 3, 4, 5. 5? Well, that's absolutely correct.
How can he do all those things, Jim?
He's full of motors, gears, cams, and photoelectric cells. You could fill a book with all the electromechanical principles involved in the thing.
The robot appeared intelligent, but in fact its actions were dictated by an electric eye that triggered preset responses.
And folks, he's only 2 years old, too. Just learning.
Since the days of Electro, mechanical men and beasts have become entertainment fixtures. In films and in theme parks such as Universal's Jurassic Park ride, robots have reached a frighteningly high level of realism.
Hey, creeps! How are you enjoying it so far? Shows like this are designed to give all you people, if you'll forgive the expression, Goosebumps!
The Crypt Keeper of Tales from the Crypt is a state-of-the-art artificial human, or artificial inhuman, as the case may be. The robot's movements are guided by an off-screen operator. A cage around the operator's head contains sensors that track the movements of his head and face. The robot mirrors his actions.
You know, kiddies, I have a great deal in common with the Phantom of the Opera.
The Crypt Keeper's dialogue emerges in a convincing way from its silicone lips, thanks to sophisticated software and dozens of mechanical muscles buried beneath its skin.
Hey, what's going on up there?
The Crypt Keeper was built by a California company called AVG. AVG started out as a maker of industrial robots, specifically machines that sewed up car upholstery. But after creating a few androids for the movies, they left the dull side of robotics behind for the glamour of Hollywood. Now AVG builds entertainment robots for museums and amusement parks around the world. The company has designed creatures of all shapes and sizes. Unlike the robots you'll find at NASA, these machines aren't assembled in sterile laboratories. AVG's humanoids start out as plaster casts. This is a mold for a prehistoric woman being created for a Japanese museum. The white goop being painted on a cast of her arms will quickly turn into soft silicone skin. Eventually, that skin will be stretched over a robot body, similar to this humanoid's. He's called Mr. Tech, and unlike conventional robots, he's powered by air pressure, not electricity. Having air for blood makes his movements smooth, and it makes him less prone to breaking down. In the world of theme parks, where humanoids run through set routines thousands of times a year, reliability is essential. But Mr. Tech is really just an actor, playing a limited part from which he can never deviate. Will we ever build a humanoid that can think for itself? Can we build machines that not only look like humans, but behave like humans? As is often the case in robotics, opinions differ. But in the United States, and especially in Japan, engineers and scientists are making significant progress in the quest to create an artificial man. Tokyo's Aikibukuro district is a showplace for the latest consumer technology. Here, hundreds of thousands of devices are sold at bargain prices to consumers with a seemingly bottomless appetite for the newest, fastest, and most elegant machines. It's no surprise, then, to learn that Japan has the largest population of robots in the world, more than 7 times as many as the runner-up, the United States. The fascination with humanoids that runs through Japan's popular culture is reflected in the real-life efforts of its engineers. Japan has launched a long-term project to create a silicone underclass of domestic servants, robot butlers, robot housekeepers, and robot nurses, and they believe it's essential that those robots are humanoids. This is Ality 2. It was built at Tokyo's Waseda University. It's designed to react to stimuli the way humans do. In this case, it has been programmed to display emotional responses to the intensity of a light. Ality is the finest product so far of a nationwide technological push called the Humanoid Project.
このヒューマノイドプロジェクトでは In the Humanoid project, we theorize that in the 21st century, humans, robots, and cyborgs will coexist within society. When that time comes, we think that it's desirable for the robot to look just like a human. We think that because of this robot's human-like movements, we can achieve a much smoother communication between humans and machines.
Alidy's big eyes and gentle movements are deliberately childlike. As robots grow more intelligent and functional, their bland, ugly exteriors are becoming problematic. The Japanese solution is to give their robots human form and to make sure they're cute. At the Science University of Tokyo, Professor Fumio Hara has created a robot that can recognize and display facial expressions. The robot scans the face of the person looking at it, comparing the distances between the eyes, mouth, nose, and eyebrows against an expressionless face in its memory bank. When the robot has locked onto a particular emotion, tiny machines push around the silicone skin of its face to mirror the mood of the person in front of its cameras.
いいかもしれないよ。なんかやらないと。そういう時に。This
project was started in order to improve the relationship between humans and robots by improving robots' facial expressions. If robots are not easily accepted by people, especially by older people, they cannot work for people. That is why we are trying to create a robot that is acceptable to the elderly.
When everything is working correctly, the face robot can reflect 6 emotional states. Today, the robot is only willing to show surprise and sadness.
Okay. Surprise. Large eyes, a little bit mouth open. Okay. Sadness. Sadness. Okay. Yeah. Halfly closed eyes. That is a sad face.
Hara's success with this prototype has created enough excitement to generate $3 million of funding for an upgraded descendant. His next goal is to give the robot a voice. Work on a mouth robot, complete with tongue, is already underway. Of course, there's more to life than having a pretty face. It also helps to have a strong, well-coordinated body. The grace and power built into the animal kingdom has inspired engineers for millennia, but we have only begun to understand how to replicate the ingenious designs of the natural world. Until recently, the seemingly simple act of walking on 2 legs has been an unbreakable barrier for humanoids. But at Waseda University in Tokyo, that wall has been shattered. This bipedal walking robot goes by the name of Wabian. It's another creation of the Humanoid project.
Hi.
Wabian can walk short distances without support. But he also weighs 600 pounds, so his student minders aren't taking any chances. Wabian also dances. He's a little stiff, but then so are most engineers. The basic theory behind the machine's springing gait has found its way into the most advanced humanoid on the planet, another product of Japan. No, that's not an astronaut in a spacesuit. You are looking at the Honda Humanoid, the closest thing yet to the androids of science fiction. The Humanoid sees through twin cameras in its helmet. Its backpack contains its power supply and computer brain. The result of a top-secret, 10 years and counting effort by the Honda Motor Company. The Humanoid does things that until recently even the most ambitious roboticist would have thought impossible. It can walk across this corporate lobby without banging into the potted plants. And more significantly, it can safely negotiate this flight of stairs. The Humanoid controls its own walk, but its hands are remotely operated. It is intended to work alongside humans in the factories of the future. In another 10 years, when the project is complete, the entire machine will be controlled by simple voice commands, such as, pick up that car. The Japanese are the clear leaders in building humanoid bodies. But who's building the robot brains? When it comes to putting brains inside the box, all eyes turn to the Massachusetts Institute of Technology's Artificial Intelligence Lab. Since the 1960s, the lab has been the center of machine learning. It's here that the one-time bad boy of the artificial intelligence world is attempting to bridge the gap between mind and body. As the pioneer of bottom-up robotics, which emulates insects and other creatures at the bottom of the food chain, Rodney Brooks might seem the man least likely to build a humanoid. But to Brooks, the creation of an artificial human is the ultimate challenge.
We'd spent about 10 years developing insect-like robots. The next logical step for me would have been to build a robotic reptile, maybe, and then after that a small robotic mammal, and then maybe a dog-sized mammal, and then maybe an ape-like, and then maybe a human. But each of these has taken 10 years, it seemed to me. It took 10 years for insects. I could see my mortality, my own mortality come up, so I thought I should try and jump some levels. And then why not go all the way? Why not go for trying to build a humanoid while I still had it in me? This is our robot Cog, which is designed to be like a humanoid, or like a human, and have the same sort of bodily shape and form as a human. It's got eyes up here which should respond to motion right now. It's looking to see when something moves, and then it tries to reach out to it. And when it first started a few hours ago, it always reached the same spot. But over time, it first learned how to make its eyes look right at something that's moving, and I'll just wait here and I move over here, then it looks over to where I'm moving, and now it's going to try and reach out to that. So when it first started, it didn't really know how to look at motion, and it didn't really know how to reach for that motion, but over time it's learnt those two things. Much as a human child, an infant, learns over the first few weeks of life how to coordinate its eyes with what it sees, and then how to coordinate its stubby little arms and reach out towards things. The arm, by the way, is not a conventional robot arm. We've modeled it very much after the human arm. In the human arm, we have springy muscles. Here we've got springs built into the system, but they're virtual springs rather than physical springs. And so we can control the stiffness of the system. And whereas a conventional robot arm in a factory, if it did something like that to me, there would be blood spurting and bone chips going everywhere. Because we're controlling the stiffness of the system most of the time. It's safe to interact with this robot in a way that we couldn't interact with a robot in a factory.
Cog was built to test an intriguing theory that there's more to intelligence than just having a brain.
Is he cuddly?
Yeah.
How does he feel on the video?
Our minds are directly connected to our bodies. Our senses of touch, taste, smell, hearing, and sight play a large part in the way we learn about our world.
Take those.
Previous attempts to build thinking machines have focused entirely on creating disembodied intelligence. But Cog creates a direct link between the digital world and the natural world. It imitates the natural patterns of learning we see in highly complex creatures, such as our children.
Is that
a match?
No. My turn.
A lot of what goes on in human development, child development, is socialization, interaction with people. And those sorts of interactions happen because we both have human bodies. We can make eye contact with each other. When I'm talking to someone and they nod their head, that's the same as me nodding my head. There's a mapping between our bodies.
Good one. Okay.
We had one example. Cynthia Farrell, one of the graduate students who designed the robot, was interacting with it just so we could get some video footage for a conference on the arm moving about. When we looked at that footage afterwards, we saw that Cynthia and the robot were taking turns playing with a racer, border racer that we had there. The robot had no notion at that stage of taking turns. But Cynthia knew how to take turns. She capitalized on the dynamics of the robot, and out of that came this turn-taking behavior. Very much like mothers playing with their children lead them through behaviors that they're not capable of generating themselves yet. So it seems to us that people cannot but help themselves interacting with artifacts in the way they interact with people. That's just built into us.
Whether or not COG will pave the way to a new form of artificial intelligence remains to be seen. But at the very least, he shows that humans relate to mechanical versions of themselves differently than they do to the equally powerful but less glamorous technology that surrounds us. More and more of that technology uses artificial intelligence, also known as AI. These are not the talking, self-conscious computers of our dreams. The failure to create artificial human brains has forced the field of AI into more practical directions.
Well, I think, there's a common belief that AI died in the late 70s and early 80s. And I think one of the things to keep in mind is that all of the applications that have come out of AI research as a byproduct are essentially embedded intelligence. They're either special purpose computers like the DSP chips in your anti-lock braking system or in your 100,000 mile without a tune-up Ford. They're in the network servers that allow you to go into any ATM in the world and get your money out. There's AI everywhere.
And looking at Gary Kasparov now, he does not look like a happy man. And now,
the triumph of IBM's Deep Blue served as a reminder that computers and computer programmers are slowly surmounting the stumbling blocks that have crippled machine learning.
He sees all these variations, and he has resigned. The IBM program Deep Blue has defeated world champion Gary Kasparov.
Deep Blue is technically not artificial intelligence. It is essentially an extremely competent calculator that's capable of making intelligent choices. But whatever you call it, the fact remains that it defeated the finest chess player alive. Apologists for the human race may argue that without consciousness, Deep Blue is still no equal for human brains. But the point was not to equal all human functions. The point was to outperform a human at a very specific task, and the machine succeeded. At a time when computer processor power is still exponentially increasing, it seems clear that our creations are gaining ground and going past their creators. There is a great difference between building an extremely clever computer and a machine that is self-aware. But do we really want machines to be able to contemplate their mechanical navels? As science fiction movies have preached for years, machine consciousness is not necessarily a good thing.
This is the voice of world control. I bring you peace. It may be the peace of plenty and content, or the peace of unburied death. The choice is yours. Obey me and live, or disobey and die.
The frightening story of the day man built himself out of existence. Colossus. Sees all, senses all, knows all, controls all armaments and all defenses. When this emotionless creation becomes the master of man, the result is catastrophic. They built Colossus, supercomputer with a mind of its own. Then they had to fight it for the world.
I think most people tend to think of intelligent machines as being conscious, conscious the way you and I are. The problem is that most artificial intelligence applications are not dealing with consciousness. They're dealing with intelligence, and there's a tremendous gap between consciousness and intelligence. Animals have tremendous amounts of intelligence in order to survive, in order to adapt to changing circumstances, changing environments, but they don't necessarily have consciousness as we, as human beings, believe we're endowed with this.
Human brain function has proven harder to imitate than the pioneers of artificial intelligence believed. The 100 billion neurons in our brains are hardwired into our bodies in a way that still baffles researchers. Our ability to sense our environments and make quick decisions has grown out of millions of years of evolution, spurred on by our competitive instinct to survive. Would it be possible to accelerate machine learning by building emotions and a survival instinct into their programs? Or should we accept the fact that machines think in a completely different way than humans? And perhaps that's all for the best. Professor Shigeo Hirose of the Tokyo Institute of Technology is one of the foremost roboticists in the world. He has built creatures of all shapes and sizes, with the exception of humanoids. The professor feels strongly that machines should remain machines.
If we try to create a slave race of exact replicas of human beings, and we give them emotions, we end up suppressing their desire to live. If that happens, everybody starts having a fear that one day the master and slave relationship will collapse, and something like Spartacus's rebellion might occur. But if we create a machine that is not human-like, we can avoid this problem.
New acquisitions. You are a protocol droid, are you not? I am C-3PO, human yes or no will do.
This is another argument in robotics. If we create intelligent machines, do we have the right to treat them as slaves?
We have been without an interpreter since our master got angry with our last protocol droid and disintegrated him. Disintegrated? God.
There's a big difference between intelligent robots and human beings if they're both working for you as slaves. Human beings carry with them an evolutionary heritage which involves wanting to survive on your own terms, essentially, for the benefit of your own genes and also your own tribal culture. The robots don't have that. The robots are built from a blank slate. Everything the robot wants to do and doesn't want to do is put in when the robot is built. The robots will no more want to be free than you would want to not eat or to not breathe. So I think the question of morality of keeping even super intelligent machines as slaves is a little bit moot.
A little family out for a walk. What do you expect? Wild robots must be free.
In the remote reaches of New Mexico, a band of scientists are taking a wildly different approach to the problem of robot intelligence. They are attempting to use the young science of chaos theory to create living machines. This is the robotic face of a field called artificial life. Dr. Chris Langton is considered the father of artificial life. He builds simulated organisms inside his computer and watches them evolve. Langton and his colleagues are trying to unravel the mystery of how life is created.
The molecular biology of the last 40 years or so has given us a very good understanding of how the lowest level bits and pieces of biological organisms work. What we do not have a very good understanding of yet is how all of those pieces work together to form one big organism. Computers have really given us the tool to understand how a whole organism is synthesized.
Yeah, it's meant for desert terrain. This is not the world's prettiest design, but it certainly is effective.
The mechanical insects created by engineer Mark Tilden and physicist Brossel Haslager are the first machines to apply the theories of artificial life to robots. These machines are all reflexes and no brains. Unlike conventional robots, they are not driven by digital technology. Their spark comes from the analog patterns of nature.
How many transistors on this? A total of about 60. So there's barely enough on this thing to make a good, decent radio.
The interesting thing between my technology and other types of roboticist technology is based upon the digital versus analog design aspects. My devices do in 12 transistors what many people can't do in 12 computers. Now, why is this? Well, let's take a look at the biological data. There's not a single living thing on this planet that has a digital computer as a brain. They all have analog systems. Yet what we've tried to do in a lot of things, like everything from artificial intelligence to even conventional robotics, is try and mimic analog processes in the digital domain. Well, this is sort of like the speed of light limit. I mean, we're already approaching that with our technology. The chances that we are also approaching the analog limit in digital technology means that I think that we are not going to be able to make competent full robot bodies that use just strictly digital electronics. So I started doing all my evolution exactly upon that sort of basis. I started out with the simplest possible analog creature I could, and I have evolved from that device, from one creature up to over 200 interactive living machines, as we call them, inside my Robot Jurassic Park. And that is my basic philosophy. And the technology that comes from that is because the robots evolve these things because they need them, not because I programmed it in.
This is Walkman. Now, Walkman, okay, I'm going to turn off Walkman now. When Walkman started up, you notice he staggered for a fraction of a second, and within a step and a half, this animal learned to walk. And this thing is not a toy in the sense that if it bangs into an object, it will adapt and try to find a way out toward a target, let's say a source of light. It does this with no computers. It does this with a very small number of transistors. These are machines that are close to alive, as close as any machine has ever come to being alive. They're survival platforms. Their only purpose in life is to survive, and so they are amazing animals. And I call them animals because after a while you get to think of them as alive. And so Walkman, which is in free space, doesn't do anything very interesting, but as soon as it comes in contact with the world, I can grab Walkman. I can, unlike most robots, I can touch him. I can try to stop him from walking. He'll fight me. He adapts. He begins to change his gait. You can see his structure turning. He completely changes his behavior. So depending on the external world completes the architecture of this machine. He's now completely annoyed, and he wants to get out of my hand, so he's flashing his lights to see where I am.
Walkman and its cousins are driven by simple urges. They're often solar-powered, so they seek out the life-giving rays of the sun. They are also inexpensive and relatively easy to build. Most of their parts are scavenged from discarded personal stereos, pocket calculators, and children's toys. Their low cost makes them expendable, but putting them out of action is easier said than done. These robots are built to take a beating. Tilden calls it biosurvivability.
The concept of biosurvivability is one that I'm trying to get inside my machines. That is, you make a device which fights for its survival, and then you trick it into doing a task for you later on. That is, you trick it into doing a task in the same way that you put blinders on an ox to get it to pull a plow. You stick special sensors on a robot to get it to cut your grass. But in all cases, it means that if you've got something like a robot that is chewed up by your dog, even though it's sick and hurt and damaged, its survivability still forces it to do a task, even if it's undergone real problems. And this is a real difference from sort of like standard digital techniques, which are a bit flip and a wire cut away from immobility. My robots can be horribly mangled, and they still do their job.
These artificial animals lack higher brain function, but they're far from simple. They do a vast amount of calculating, but on a level so deep it approaches chaos. Chaos is a name for the underlying complexity that's built into the seemingly random patterns of nature. The mathematics driving this are difficult for most humans to grasp, but the result is a machine that functions more like a natural organism than a man-made construct.
This is Snake, and Snake is the most unusual creature. It's actually quite frightening. I'm holding it now in my hand, and Snake is reacting to me in various modes. It can spin like so. It can move along its length like a regular snake, but mostly it's not walking. This thing is moving through its environment by using modes of movement that biology, for the most part, never implemented. So Snake is really the first truly alien creature of this family of parallel life machines. And if you held it in your hands, you would see why.
One of the critical arenas in which I think artificial life is really going to contribute is in understanding the way in which biological machines are engineered as opposed to the way that we classically tend to engineer machines. On the scale of geological time, over which we typically measure evolution, we are literally at now the end of one biological era and at the beginning of a new one. As soon as we attain the capability to actually synthesize life from scratch, whether it's in a beaker or in a computer or with a robot, we will have introduced into the world a whole new lineage of life, one that was synthesized by human beings instead of having just emerged from nature. I'm going to bet that by the year 2000 or within a decade of then, we will have built a machine that satisfies most of the criteria that biologists currently apply to living organisms.
At the beginning of a new millennium, humanity finds itself hurtling into a wired world where intelligent systems are integrated into every part of our daily lives. But what path will robots take? Will our creations remain unintelligent and unaware, capable only of following simple commands? Or will they evolve into a unique new form of life, able to reproduce and survive without our support? Will friendly humanoids serve us dinner? Or will killing machines run wild?
I certainly believe that we are machines, so in principle there's no reason that we can't ultimately build a self-reproducing intelligent robot.
We're close to mastering the technology of life, a lot closer than we are to understanding the consequences of mastering that technology.
We always think that, oh my goodness, it's going to go after Sarah Connor. But in actual fact, there is never going to be, in the general environment, robots that are smarter than we are. We are always going to be able to trick them or stop them.
作れればいいんですけども、それはそう簡単には
Technically speaking, it might be possible to accomplish the goal of creating a self-replicating robot within 100 years or so. Whether these robots will become one of the species or tribes on this earth is an extremely difficult question, because a robot is basically designed and created by the hands of a human being. I think it all depends on the human's intention. In other words, whether we want to design robots with that kind of ability. If we decide to design robots that are self-evolving, what can we do to prevent them from becoming a threat to humanity? I think this is a big issue which our society has to determine in the future.
結論を出していかないといけない問題だと思いますけども。
At Pittsburgh's Carnegie Mellon University, Hans Moravec has been studying the consequences of robotic evolution. Moravec feels that humanity is at the brink of a golden age, and we had better get ready for it.
I've compared the progress of robots and computers with the evolution of biological intelligence and come to the conclusion that it's going about 10 million times faster, and that we're just at the beginning of the vertebrate stage, effectively. But because of the pace, we can expect a machine that can not only model its world, but can reason abstractly about it. And that machine, I think, is comparable to human beings. In fact, in some ways, it will undoubtedly be much better than human beings, because it'll do those things better that we do very, very poorly. For instance, arithmetic, but also logical reasoning of long chains of reasoning, and also communicating and sorting large databases and so on. So what we'll have is a machine that can get around the world about as well as we do, but that can basically think better than we do. And at that point, human beings are on the verge of obsolescence.
This plant in Japan is nearly completely automated. Moravec believes that when our robots can design and build themselves, all industry will look like this. Eventually, we'll all be unemployed. But there's a bright side. If the super competitive companies staffed by these robots are taxed, we will all be born rich from a kind of cybernetic social security.
A world in which the robots are doing all the work and, in fact, straining their superintelligence to try to please us better, to sell us products so that they can pay their taxes, I think will not be quite as strange as it sounds, because it's not so different from the world in which we evolved in for a period of several million years, when we lived in tribes of hunter-gatherers. Because at that time, essentially, there was an automated economy working for us. It was called the ecology. And our activities mostly consisted of going out into that ecology and getting the things we needed for our lives, especially food. Shopping is not that different from hunter-gathering.
But for now, robots are confined to menial jobs, and some insist they'll stay there.
The fear that we're going to create a race of super intelligent, super smart, super powerful androids that will take care of everything and put everybody out of work is a ridiculous concept. I mean, I think that what's going to happen is we're going to not be competing with the androids. The androids are going to do the things that androids do best. People are going to do the things that they do best, which may just be watching more television, surfing the World Wide Web.
There's going to be all sorts of different looking robots depending on what their task is. There'll be robots embedded in our houses, watching us, making some decision and doing something based on those decisions. And they won't appear anything like the way we think about robots today. I think there'll be other robots which will have human form and which we will be interacting with, because if the hypothesis is right, that it takes the human body and those sorts of experiences to be like a human, all the other robots will be aliens to us. They won't be things we can relate to. The only ones we'll be able to relate to are the ones which have humanoid form.
Technology is an incarnation of the human urge to survive and prosper. Our machines help us to overcome our limitations. Endowing our robots with intelligence is the next step in our ongoing effort to make our lives easier. But as our creations grow ever more complex and self-reliant, our fear of technology grows. We surround ourselves with high-tech tools, but we don't quite trust them. But living machines, even artificial humans, may turn out to be less alien than airplanes or television sets. All of the complex devices we depend on, but don't really understand. Perhaps, by making our machines more like ourselves, we are bridging the gap between creation and creator.